Let's start with internal energy. The change in the internal energy of a system is equal to Q plus W. Now, Q represents the amount of heat energy that enters or leaves the system. So here's a question for you. Let's say if inside the box represents the system, and let's say the outside, anything outside the box is the surroundings. Now let's say the temperature of the system is 100 degrees Celsius, but the surroundings is only 50 degrees Celsius. Well, actually, let's say 25. Now, will Q be positive or negative? Heat flows from hot to cold, so heat is going to flow out of the system into the surroundings. So Q, relative to the system, is going to be negative. Q is negative. Whenever heat is released from the system, it's considered to be an exothermic process. Now, for the surroundings absorb heat energy, so Q is positive for the surroundings. So it's endothermic for the surroundings. Anytime heat is absorbed, Q is positive. Typically, Q is measured in joules. Now you need to know that 1 kilojoule is equal to 1,000 joules. And a calorie, a lowercase calorie, that's 4.184 joules. A capital calorie is 1,000 lowercase calories. So those are some other conversion factors you need to know. W represents work. And work is equal to negative P delta V. When work is done on a system, W is positive. Whenever work is done on a system. Now, if work is done by the system, W is negative. Now, for this equation, W equals negative P delta V. When the change in volume is positive, whenever a gas expands, the work is negative due to this negative sign. And so whenever a gas expands, it can do work. It can exert a force to move a piston or something. Now, to compress a gas, you need to apply a force. So whenever gas is compressed, the change in volume is negative, so the work overall is positive. So as you apply a force to compress the gas, you're performing work on the system. So the internal energy of the system goes up whenever you do work on it. But whenever the system does work, or whenever work is done by the system, the internal energy of the system goes down. It loses potential energy because it's using up energy to do work. So let's see if we can apply this information in a practice problem. But before we do, another thing you need to know is that 101.3 joules is equal to 1 liter times 1 ATM. So now, let's say if 300 joules of heat energy was absorbed by the system, and also, let's say the system, which is a gas, let's say the gas expands from 2 liters to 3 liters at a pressure of 5 atm. Calculate the change in the internal energy of the system. So the first thing we need to do is use this equation. W is equal to negative P delta V. The pressure is 5 atm. The change in volume, final minus initial, it's 3 minus 2. So P delta V is going to be negative 5. And the units is going to be liters times atm. Now, in order to get delta E, we need to convert liters times atm into joules. And as we mentioned earlier, 1 liter times 1 atm is equal to 101.3 joules. So the units, liters, cancel, and atm cancel as well. So what's 5 times 101.3? 5 times 100 is 500. 5 times 1 is 5, and 5 times 0.3. If 5 times 3 is 15, 5 times 0.3 is 1.5. So this is going to be negative 506.5. If you add 500 plus 5 plus 1.5. So that's how many joules of work that has been done by the system. So that's why W is negative, because the gas expanded and the gas performed work. So the internal energy of the system went down. So now we can calculate everything. Let's plug in what we have into the delta E equation. So since heat energy is absorbed, it's endothermic. Q is positive 300, and W is negative 506.5. So 300 minus 506.5, that's going to be equal to negative 206.5 joules. So that's how much energy the system lost overall. So now there's some other equations that you need to know. Q can be calculated using the equation mc delta T. M is the mass, C is the specific heat capacity, and in the case of water, it's 4.184 joules per gram per Celsius. So what this means is that if you have a 1 gram sample of water, it takes 4.18 joules to heat up that 1 gram sample of water by 1 degree Celsius. Delta T is the change in temperature, which could be in Kelvin or Celsius. So let's say if you want to calculate, the amount of energy that's required to heat up, let's say 50 grams of water from 25 degrees Celsius to 75 degrees Celsius. How much energy is required? So the mass is 50, the heat capacity of water is 4.184, and the change in temperature, final minus initial, 75 minus 25, that's 50. So if you have a calculator, 50 times 50 is 2,500, and if you multiply that by 4.184, you should get 10,460 joules. So that's how much heat energy is required to heat up 50 grams of water from 25 degrees Celsius to 75 degrees Celsius. And if you divide this by 1,000, you could convert your answer into kilojoules if you want to. So whenever you want to calculate the amount of heat energy absorbed or released whenever there's a temperature change, use the equation Q equals MCAP. Now, whenever you want to calculate the amount of heat energy that's absorbed or released whenever there's a phase change, you can use the equation Q equals M times delta H. This could be enthalpy of fusion or vaporization,